Title of my talk, Plastic Strain-Induced Phase Transformations under High Pressure for Scale Theory, Experiments and Phenomena. I would like to acknowledge my collaborators and funding agencies. I will start with description of our experiments in a unique device, rotational diamond anvil cell. And for understanding and interpretation of these experiments, we developed four-scale theory. At atomistic scale, we use molecular dynamics and DFT to find lattice phase transformation criteria on the action of all 6 components of stress tensor. At the nanoscale, we use molecular dynamics and also develop nanoscale phase field approach to study interaction between discrete dislocations and phase transition. And at the microscale, we develop completely different microscale phase field approach to solution of the same problem, and also use micromechanics to derive a kinetic equation for strain-induced phase transformation, which we use as part of our macroscale model. And we apply this model to describe behavior of sample in rotational diamond anvil cell. Each lab has a diamond anvil cell, 2 diamonds, compressed sample within gasket, without gasket. And what we are doing differently after compression, we twist one of anvils, superposing large plastic shear. And this changes everything. We perform our experiment in our lab at Iowa State, but mostly at synchrotron radiation facility at APS. What we measure? We measure radial distribution of pressure in each phases. You see here in hexagonal and versitic boron nitride, and they differ by factor 2 or by 6 GPa, which is, so it's important to know both. Then we measure distribution of volume fraction of high pressure phase, of phases, and defects, turbostratic stacking fault, this dislocation density, crystallite size. We use X-ray absorption to find thickness profile of sample. And we place Ruby particles from both sides of sample and measure not only pressure, but also displacement of particles. And this is important because, for example, at rotation of angle of 10 degrees of anvil, rotation of material is just 2 degrees. Well, there are many phenomena. We will focus on 2 of them. First, plastic shear significantly reduces phase transition pressure. And you see, for phase transition from hexagonal to versitic boron nitride, we obtain this transition at 6.7 GPa under torsion, and it does not occur under compression even at 23 GPa. The same for rhombohedral to cubic boron nitride, 5.6 versus 55, order of magnitude difference. Alpha to omega zirconium, 0.67 versus 6. Silicon 1 to silicon 2, 0.4 versus 16.2. And silicon 2 to silicon 3, 1.9. And it does not occur on the hydrostatic loading. So huge effect. Also, plastic shear leads to new phases, which cannot be obtained under hydrostatic conditions. Here is an example of new high-density amorphous phase of silicon carbide, which you obtain at 30 GPa and large shear. And under hydrostatic condition, amorphization was not observed even at 135 GPa. Also, recently we discovered new super high disordered phase of boron nitride. You see it scratches diamond. And we detected it with X-ray and Raman. Point is that macroscopic thermodynamics cannot describe any of this phenomenon. And the reason is that shear stress is limited by macroscopic yield strength in shear, say 1 GPa. And this is the mechanical driving force for phase transition. And under some assumption, pressure and shear are additive. And say at 50 GPa, effect of 1 GPa of shear is 2%. We can change assumption, we will get 10%. but we never will get order of magnitude reduction. And that is why we develop our four-scale theory. At the atomistic scale, our goal is to find phase transformation criteria on the action of 6 components of stress tensor, which sounds impossible because of large number combination. But first we develop a continuum phased field approach and derive such criteria analytically. And now it's we need just to prove it. So this is a criterion under such loading. And key point is that it's linear in stresses. So in space sigma 1, sigma 2, sigma 3, it's plane. And we rotate this picture until plane is visible as line. And green dots are results of MD simulation, and here results of the AFT. You see very strong proof of our criterion. And also we calibrated two material parameters. When we apply, in addition, 3 shear stresses, we get additional term here, but without new constants. And again, we obtain the deviation of MD and DFT results from our analytical expression is within 5%. So now we have analytical expression at 6 components of stress tensor. It's far beyond of what was known in literature, maximum 2, in rare cases, 3 components. We also developed 5th degree elastic potential for silicon, and you see that predicted stress strain curve are in good correspondence with DFT results, even to for large strains. And one example. So on the hydrostatic condition, phase transition pressure for silicon 2 to silicon 1 to silicon 2 is 67 GPa. And the uniaxial loading is already 11. And mean pressure is 3 times smaller, so there is 20 times reduction in hydrostatic pressure. Problem is one cannot apply uniaxial 11 GPa because real material yield strength of real material is much lower. But such stresses will be realized at the tip of strong defects. And we developed phased field approach to treat this problem. But first, point is that high pressure community before our paper didn't realize that there are 2 completely different types of phase transformation. Pressure-induced phase transformation, which starts at pre-existing defects, which represent stress concentrator. And we study now strain-induced phase transformation, which started new defects permanently generated during plastic flow. And they represent defect-induced phase transformation. It requires completely different thermodynamic and kinetic description and experimental characterization. And we consider material and the hydrostatic pressure. Phase transition pressure is, equilibrium pressure is 10 GPa. With one dislocation, material transforms at 16 GPa. And then we consider bicrystal under compression and shear, and dislocation, nucleate, and pile up against grain boundary. And here at the tip, our phase, and they produce strong stress concentrator of all components of stress tensor proportional to number of dislocation. And here there is huge stress concentrator, and that is why our criterion is satisfied here. And it's satisfied at pressure, which is just 1.2 GPa. So this is conceptual proof that dislocation pile up can reduce pressure by order of magnitude, more than order of magnitude in comparison with pressure under hydrostatic condition, and almost order of magnitude in comparison with phase equilibrium condition. And you see with increasing shear, we obtain quite large amount of high pressure phase, but this is with neglected dislocation in this grain. If we allow dislocation, then you see transform region is much smaller. So plasticity plays dual role. It promotes phase transition by increasing stress concentrators, but it also suppresses phase transition by relaxing the stress concentrator. And we found some combination of pressure and shear, that solution without dislocation and with dislocations are the same. So it's controllable. And we formulated our nanoscale results and new possible routes for defect-induced material synthesis under high pressure. This is first atomistic proof of pile-up dislocation pileup induced phase transition. This is amorphization in silicon and square to hexagonal phase transition. You see pileup, nucleation of new phase, which is here. And also what is important, that dislocation produce large step at grain boundaries and work like super dislocation. So this stress concentrator is not dependent of grain size. Main problem with nanoscale phase field approach that it should resolve numerically with finite elements interface width, which is 1 nanometer. And that means that we cannot treat large samples. That is why we develop completely different scale-free phase field approach. And we can take into account also, we took into account also different crystallographical equivalent martensitic variants of high pressure phases. And dislocation pileups are introduced through solution of contact problem of continuum mechanics, because we still need stress concentrator. And you see this is evolution of dislocation in polycrystalline sample, and red is high pressure phase. And this is evolution of first and second martensitic variants. And you see that in each grain we have very different kinetics, and we also determine kinetics average over the entire sample for high pressure phase for each variant and pressure, shear stress. And based on this information, we are currently developing kinetic model for microscale. But at the moment, we use our old model, which still takes into account all what we learned at the nanoscale. In particular, the effect generate both compressive and tensile pressure of the same magnitude. That is why they simultaneously promote both direct and reverse phase transition in different regions. Also, nucleation was barrierless. We don't need to wait for thermal fluctuations. That is why time is not parameter, and accumulated plastic strain plays a role of time-like parameter. This is for direct phase transition, for reverse phase transition. And finally, plastic strain localizes in a wiki phase. And we develop very simple model for portioning of plastic strain between phases, which depend on ratio of yield strengths of phases. And that is why our kinetic equation also depends on ratio of yield strengths of phases. And this equation allows us to explain and even predict a lot of phenomena. But today I want to discuss its first experimental confirmation for alpha to omega phase transformation in severely predeformed zirconium. Severely predeformed means that we subject zirconium to rolling until it hardness saturated at reach steady state. And this is very important. So we don't have reverse phase transition. This is our equation. This is phase transition pressure under hydrostatic condition, minimum pressure for plastic strain-induced phase transition, and you see that it's 4.5 times smaller than under hydrostatic condition and almost 3 times smaller than phase equilibrium pressure. And in 3 experiments, we produce 3 pressure plastic strain passes. This is volume fraction of omega phase. Line is our equation, and all experiments are very close to this equation. So this is first experimental proof of validity of our equation. It took just 20 years. Also, we calibrated material parameters. And you see that our kinetic equation is independent of pressure plastic strain path. And also we varied initial thickness of sample and rolling process. And kinetics is also independent of this process of plastic strain before phase transition. Here's pressure distributions. And these boxes show minimum pressure for initiation of phase transition, 1.2 GP. And you see that it's independent of radius. But plastic strain increases significantly with radius, and also plastic strain path completely changes. Here we have just compression without shear, and shear increases with increasing radius. And that means that minimum pressure for plastic strain-induced phase transition is independent of plastic strain and plastic strain path. This is very important rule, and it has immediately important consequence that strain-induced phase transition under compression in diamond cell and shear in rotational diamond cell don't fundamentally differ, and in terms of kinetic and consequently mechanism and modeling. Main problem in studying phase transformation, plasticity, microstructure evolution is that response depends on all 5 components of stress tensor, which already makes chances to get some general loss very small, but it also depends on entire plastic strain path, which reduces hope to 0. And still, what we found is actually first law for plastic strain-induced phase transition under severe plastic deformation. The minimum pressure, it's independent of plastic strain and plastic strain path. But even more, we found that also dislocation density and crystallite size and yield strength are also independent of plastic strain and plastic strain path. To find this for yield strengths, we developed diamond anvil cell with rough diamond, and rough diamonds produce maximum possible friction equal to yield strength and shear. That is why we can easily find pressure dependence of yield strength. And you see that yield strength is independent of plastic strain and plastic strain path, but still with this expression, solid line are theoretical lines, and they describe well all experimental curves, despite the fact that at each point of this curve, we have completely different plastic strain and plastic strain path. But even more, during phase transition, dislocation density and crystallite size depends solely on volume fraction of omega phase and are independent of plastic strain path, and even pressure. So this plethora of results represent new laws for plastic strain microstructure evolution and plastic strain induced phase transformations. And they were obtained in a single experiment, and thus transforming the main challenge, strongly heterogeneous field in diamond anvil cell, into great opportunity. And also these steady plastic strain independent states are different for a rough and smooth diamond. Also, we have another third steady state after rolling. But with rough diamonds, dislocation density is larger than for smooth diamond, and grain size is smaller. And this explains why phase transformation pressure with rough diamond is 2 times smaller than in smooth diamond. Well, this kinetic equation is part of our macroscale model. I will not go in detail, just say that yield strength depends on pressure, plastic strain, and volume fraction. This is Murnaghan rule. And we solved many problems. I will discuss just 2 of them. This is plastic strain-induced phase transition from hexagonal to versitic boronite. Well, we already discussed that phase transition during compression in diamond cell and during torsion don't differ. And we took this into account in our model. This is minimum pressure for plastic strain-induced phase transition, which means that at slightly higher pressure, we can run phase transition to completion by applying very large plastic strain. But when we compress a sample, pressure grows along with plastic strain. And what we obtain in our modeling is that actually phase transformation is not detected below 12 GPa. And even at 53 GPa in this region, phase transition is very far from completion. And that is what experimentalists would report. and it has nothing to do with material behavior, which is here. So that means that such experiment determines system behavior rather than characteristic of phase transformation. And good point is that with rotational diamond cell, by proper optimization of sample gasket system, we can reach, we can run phase transition of plastic deformation during rotation almost at constant pressure. And we realize this in experiment. You see, this is the pressure distribution before and after rotation, before and after rotation, and before and after rotation and phase transformation. So this is doable, but also there is danger, again, in misinterpretation, that plastic shear promotes phase transition in comparison with compression. This is wrong. Correct answer is that torsion allows to produce much larger plastic strain at constant small pressure than compression, than under compression. Well, to characterize phenomena, we need to know all components of stress and plastic strain tensor, but they are not measurable. So we suggested the following approach. We measure all what can be measured, then we develop material models and determine material properties by fitting simulated results to measured field, and then verify model by independent experiments. And with this property, our finite element simulation give all fields, including components of stress and plastic strain tensor. So we solve the problem. And to prove a concept, we took experimental data from this paper. This is tungsten up to 400 GPa. We use two pressure distributions to calibrate our model. And then we use two other higher pressure distributions and for sample thickness profile to verify model. You see very good comparison. And we did not use any of these experiments. So now our model is well verified. That is why our pressure dependence of yield strength is much better than what was known in literature. We also found pressure dependence of friction coefficient and refined certain force elastic constants for diamond and tungsten. And with this calibrated and verified model, we determined all components of stress and plastic strain tensor. So this is solution to problem. And the last example, graphite to diamond. Under hydrostatic condition, phase equilibrium pressure is 2.5 GPa. Phase transition in ideal crystal occurs at 250 GPa, and experiments it's 70 GPa. And our phase field simulation predicted that actually this phase transition can be obtained at a very small pressure, and guided by these simulations, experiments were performed at very low pressure, and indeed diamond was obtained at 0.7 GPa, which is 100 times lower than under hydrostatic conditions. This is currently a record of reduction in phase transition pressure. If it can be scaled up, it can result in new strain-induced diamond synthesis technology without temperature, without catalyst, and at low pressure. But also it has implication in geophysics. Diamonds in geophysics were found in high pressure, high temperature region, but microdiamonds were also found at low pressure and temperature region in Earth's crust. And main hypothesis was that this portion of material traveled down to high pressure, high temperature region, and after phase transformation uplifts back. But since we found that diamond can be obtained at low pressure and temperature just by applying shear, then nobody needs this journey, and diamond can be directly obtained here during various tectonic events leading to shear bending. Indeed, these microdiamonds were found in severely sheared regions. And I stop at this point, place conclusion, and thank you for your attention.